Western sanctions have systematically limited China's access to key aviation components for decades. High-end sensors, precision navigation systems, advanced avionics, the technologies that make up the core of modern aerospace engineering, remained off-limits. The United States placed Chinese aerospace firms on military blacklists. Japan and South Korea tightened export rules on advanced chips and microelectronics. Almost every route to cutting-edge aviation technology appeared closed. Then came a breakthrough announcement. In December 2020, Chinese researchers revealed that they were developing an oblique detonation ramjet capable of propelling an aircraft to Mach 16. To put that into perspective, an aircraft moving at that speed could theoretically reach any point on Earth within about 2 hours of takeoff. The fastest operational aircraft today tops out at around Mach 9.8. America's most advanced civilian supersonic prototype, Unveiled, that same year only reaches roughly Mach 2.2. China's new propulsion concept operates at speeds nearly 7 times faster. This wasn't gradual improvement. This was a major rethinking of what aviation propulsion could be. But the story starts decades earlier, back in the late 1950s, when China's leadership identified aviation as a foundation of long-term national modernization. That decision immediately worried Western governments. Instead of supporting technological cooperation, the US and its allies created layers of export barriers. These restrictions targeted the essential building blocks of aerospace progress, the components that separate a functioning aircraft from a theoretical design. China's response surprised many outside observers. Instead of retreating from aviation development, engineers intensified their efforts toward domestic solutions. The first clear achievement came in 1983 with the turbojet 14 engine created for the J-8 fighter. By global standards, its capabilities were modest. The technical base was weak and performance limited. But it proved something more important than early success. It showed that independent engine development was possible. Progress continued step by step. Each engine generation taught engineers new lessons. Manufacturing quality improved. Material science advanced. By the early 2000s, China produced the Turbofan 15, using high-temperature alloys that earlier teams simply didn't have access to. Combustion performance increased and thrust output rose significantly. This engine would eventually power the J-20 stealth fighter, signaling that China had closed much of the gap in conventional jet propulsion. But, traditional jet engines operate within known physical boundaries. What China announced in 2020 existed in an entirely new realm. Oblique detonation ramjet technology relies on an extreme combustion method. Typical jet engines burn fuel through deflagration, which is a subsonic combustion process where the flame front spreads relatively slowly through the fuel-air mix. Detonation combustion, though, works very differently. It releases more than 70% of the fuel's chemical energy in a highly compressed space and time frame. The combustion wave moves supersonically, creating shock waves that massively increase energy release. Thermal efficiency can be double that of conventional engines. This isn't just a small upgrade, it's a complete shift in how chemical energy turns into thrust. Testing technology like this requires extraordinary infrastructure. NASA's X-15 wind tunnel, built during the 1960s space race, could simulate flight conditions up to Mach 15 and stood for decades as the pinnacle of hypersonic testing capability. Yet even that facility cannot match what oblique detonation ramjets require. To solve this, China built the JF-22 Hypervelocity wind tunnel. It can recreate environments at roughly Mach 30, double NASA's capacity. It is now the world's largest and most advanced ultra-high-speed wind tunnel. Inside this massive installation, engineers pushed their oblique detonation concept through conditions that would immediately destroy conventional engines. The results, honestly, outperformed expectations. Tests showed sustained operation at Mach 16. To highlight this achievement, while American engineers were celebrating the XB-1 demonstrator reaching about Mach 2.2, Chinese researchers were validating propulsion at speeds that make flights like New York to London feel like short trips. The strategic implications are enormous. An aircraft using such propulsion could take off from Beijing and arrive over Washington, Moscow, London, any major capital, within a couple of hours. Traditional air defenses are built for threats traveling at predictable subsonic or low supersonic speeds. Detection systems, interception procedures, and response timelines all break down when faced with something moving at Mach 16. The engineering innovations go far beyond sheer velocity. Traditional ramjets inject fuel directly into the intake duct, relying on incoming air compression to ignite it. This works at moderate supersonic speeds but becomes extremely unstable at higher velocities. Fuel mixes poorly. Combustion flickers. Components shake violently. Fuel consumption explodes. Chinese engineers redesign the entire fuel delivery method. Their system pre-injects fuel ahead of the intake. Shock waves from the hypersonic airflow force this mixture into the combustion chamber, where precisely timed detonation takes place. This eliminates the uneven mixing that plagues traditional ramjets. Vibrations drop dramatically. Fuel efficiency grows. Engine stability holds over a much wider speed range. Oblique detonation also addresses another problem. In conventional engines, fuel burns perpendicular to airflow, creating turbulence and incomplete combustion. Detonating at an angle aligns the combustion wave with the incoming air, allowing cleaner combustion and higher temperatures. Higher temperatures deliver greater thrust and better specific impulse, core measures of engine efficiency. These breakthroughs didn't happen overnight. Detonation-based propulsion has been discussed in aerospace circles for decades. American and Russian researchers studied similar ideas during the Cold War, pouring resources into hypersonic programs. The U.S. flew the X-43A scramjet in 2004, hitting Mach 7 for about 11 seconds before the engine lost efficiency. In 2013, the X-51A Waverider accelerated from about Mach 4.8 to over Mach 5 and held hypersonic flight for 6 minutes. It was a significant milestone, but also revealed major limitations. What makes China's advancements so remarkable isn't just the performance, it's the speed of development. Chinese research groups didn't begin serious scramjet work until around 2015. In Western aerospace engineering, hypersonic propulsion is considered one of the hardest problems ever attempted, an area where progress normally comes in small steps over decades. China compressed that timeline dramatically, going from early research to Mach 16 validation in about 5 years. This rapid progress reflects more than skilled engineers. It shows a national strategy designed to break through technological barriers. When sanctions cut off access to foreign wind tunnels, China built ones that were more capable. When advanced materials remained out of reach on global markets, Chinese metallurgists created domestic substitutes. When computational fluid dynamics software fell under export control, Chinese programmers built their own high-end simulation platforms. Aviation specialists across Western institutions have begun describing the oblique detonation breakthrough as potentially equivalent in importance to the original invention of the jet engine. That comparison may sound exaggerated until you consider the implications. Jet propulsion reshaped 20th century warfare, commerce, and geopolitics. It collapsed travel times, rewrote strategic planning, and enabled entirely new categories of military and civilian operations. Hypersonic propulsion capable of sustained Mach 16 flight could trigger a similar scale of transformation. Intercontinental trips shrink to times that make today's commercial aviation look dated. Military strike ranges expand to true global reach with almost no warning. Space access costs may drop if hypersonic craft can shift efficiently between atmospheric flight and orbital profiles. But major questions remain. Even the most advanced wind tunnel testing differs from real-world flight conditions. Thermal loads, structural stresses, and control difficulties created by prolonged Mach 16 travel through the atmosphere exceed what current materials and avionics can handle for long durations. Bridging the gap from laboratory validation to an operational aircraft requires solving thousands of engineering problems that never appear in simulations. China has not yet unveiled an aircraft using this engine, nor have any flight tests been publicly documented. The transition from successful lab tests to deployable technology often takes years or decades, especially for propulsion systems this complex. Aviation history is filled with promising propulsion ideas that never progressed beyond prototypes. And yet, dismissing China's progress would be strategically short-sighted. Similar skepticism greeted Chinese breakthroughs in stealth design, ballistic missiles, space programs, and quantum communications, until each became an operational reality. Western intelligence assessments have repeatedly misjudged Chinese aerospace timelines, assuming technological obstacles would stall progress indefinitely. Those assumptions turned out to be wrong. The geopolitical context really amplifies the importance here. For decades, American aerospace superiority acted as a foundation of global military and economic influence. That lead once looked insurmountable, measured in generations rather than years. But China's hypersonic developments now indicate that those gaps have narrowed dramatically, and in certain sectors may have disappeared completely. This shift honestly reaches beyond just military competition. Commercial aviation still operates under speed limits defined by 1970s-era technology. The Concorde flew its final commercial route in 2003, and no supersonic passenger service has existed since. Airlines and manufacturers prioritized fuel efficiency over speed, accepting that long-distance flights would take roughly the same time regardless of incremental improvements. Hypersonic propulsion could make speed a defining commercial advantage again. If Chinese engineers can convert oblique detonation technology into safe, affordable passenger aircraft, the entire structure of global aviation could be upended. Routes that today require connections might become non-stop trips measured in minutes, not hours. Business travelers might routinely attend same-day meetings on multiple continents. The broader lesson here extends well beyond aviation. Sanctions intended to slow technological progress can, paradoxically, accelerate it by forcing nations to develop complete domestic capabilities. When every critical component must be produced internally, countries build industries that remove dependence on outside suppliers. Short-term restrictions can end up creating long-term competitors with fully independent industrial ecosystems. China's aerospace sector now operates largely insulated from Western supply chain pressure. Advanced materials, precision manufacturing, test facilities, simulation software, and trained personnel all exist inside China's borders. This self-reliance provides strategic flexibility that import-dependent systems just lack. It also means future Chinese aerospace breakthroughs will not require Western approval or technological cooperation. The Oblique detonation Ramjet is just one visible sign of a broader transformation. Chinese research institutes are advancing multiple aerospace domains at once: reusable launch vehicles, high-altitude long-endurance drones, sixth-generation fighter concepts, hypersonic glide vehicles, and next-generation air defense systems. Each effort builds on shared technology bases, creating synergies that accelerate progress as a whole. Western governments and aerospace firms now face strategic decisions about how to respond. Trying to preserve technological dominance through more export controls looks increasingly ineffective, when the targeted nation has shown it can develop even superior alternatives. Collaborative approaches may offer more promising outcomes, but require accepting that U.S. aerospace dominance is no longer guaranteed. Meanwhile, the engineering challenges of sustained Mach 16 flight remain immense. Materials must endure temperatures surpassing 2,000 degrees Celsius without failing. Control surfaces must function in hypersonic airflow regimes where traditional aerodynamics collapse. Sensors must operate through plasma envelopes that block normal communications. Fuel systems must handle cryogenic propellants while adjacent structures glow red hot. China has not released detailed solutions to these problems, but the JF-22 test results indicate that workable approaches exist. Whether those solutions lead to operational aircraft in 5 years, 10 years, or longer is still unknown. What is clear is that technical barriers once viewed as impossible by Western experts are being systematically solved by Chinese engineering teams working under tight constraints. The consequences extend beyond aerospace into broader debates on innovation and national strategy. How nations allocate research budgets, organize educational systems, coordinate government-industry projects, and respond to geopolitical pressure increasingly determines their technological paths. China's aerospace achievements reflect decades of deliberate investment in STEM education, research infrastructure, and coordinated industrial planning. As this technology matures, new questions emerge about international safety standards, regulations, and arms control frameworks. Hypersonic aircraft and weapons challenge existing treaties and verification systems. Detecting and identifying threats becomes far more difficult when vehicles can strike from unexpected trajectories with almost no warning. Air traffic management designed for subsonic flight would require a complete overhaul to handle routine Mach 16 operations. The path from experimental breakthrough to operational capability still contains countless obstacles. But one fundamental question has already been settled. Sustained propulsion at 16 times the speed of sound is achievable with technologies available today. What once seemed like pure science fiction has become an engineering challenge with proven solutions. The consequences of that reality will reshape aerospace development, military planning, and global politics for decades to come.